Hi and welcome to the lesson of real analysis. So in this class, we are going to start the discussion where we left in the previous class. And we were discussing the completeness of rational numbers, and we concluded that rational numbers are not complete. Rationals are not complete because there are gaps in rationals, right? And we took an example for rationals that x belongs to the rationals where such that x square is less than 2. So this was our set, and we tried to find the least upper bound. Because the set is bounded above, we can see here x square is less than 2, which means x is less than square root of 2. So every number that is rational and it's less than square root of 2, it belongs to this set. So this set is non-empty, and we say that the completeness property is that the set has the upper bound should have the least upper bound as well. So in this case, in a least upper bound, and it should belong to the set that we are talking about. So here we can see that x belongs to the rational numbers. So uh, this root 2, that is the upper bound of the set, does not belong to the rational numbers, and we will prove in this class that y square root of 2 is not a rational number. So now that prove that square root of 2 is not rational. So we will prove it by a contradiction. And now we will start with an assumption that square root of 2 is a rational number. That assume square root of 2 is rational. So we assume that square root of 2 is rational, which means that we can write this square of 2 as p over q, where p and q are integers and they do not have any common factor. So p and q do not have any common factor. So p over q is equal to square root of 2. If we square both sides, equals 2. So p and q do not have any common factor. So this is our assumption. Now we can see that if p square equals 2q square, which shows that p square is multiple of 2, right? So it's a multiple of 2, which means that it's a number, some number 2 times some other number. That is, q square is also an integer, so 2 times some other number. So which shows that p square is divisible by 2 because it's a multiple of 2. So it's divisible by 2, and we know that if a square of some number is divisible by 2, then the number itself is also divisible by 2. So p is also divisible because p square is divisible by 2. Therefore, p is also divisible by 2. And then similarly, we can assume that if p is divisible by 2, we can say that p equals to 2 times some other integer, right? Because p is divisible by 2, so we can write p equals to 2 times some integer, and then we will plug this in equation 1. Say this is equation 1. So equation 1 implies that 2n squared equals 2q squared, and then we have 4n squared equals to 2q squared, which implies that q squared equal to 2n squared. And again, this equation suggests that q square is also divisible by 2 because it's a multiple of 2. So it's also divisible by 2. And if it's divisible by 2, then q is also divisible by 2. So we see here that both p and q are divisible by 2, which means that they both have common factor. But in our assumption, we said that p and q do not have any common factor. And this is the contradiction. So here when we started our proof, we have the assumption that p and q do not have any common factor. But at the end, we concluded that P is also divisible by 2 and Q is also divisible by 2, which means that P and Q both have the common factor. So it's not a rational number. So square root of 2 is not rational. So that's why not the square root of 2 does not belongs to the set of rational numbers, and in this case we cannot find a least upper bound. Here we cannot find a least upper bound which belongs to the set of rational numbers or which belongs to the universe of rational numbers. Okay, now let's take one more problem. Check whether square root of 7 is irrational. Irrational. So now we'll prove that this square root of 7 is irrational. And in the similar manner, I will prove by contradiction. So assume that square root of 7 is rational. Okay, we start with an assumption that square root of 7 is rational. So again, we can write, it means that if it's a rational number, then we can write square root of 7 as a ratio of the number that is in the fraction form, and where and we can write that the greatest common divisor of m and n is 1, which means that they do not have any common divisor other than 1, right? So which means that they cannot be divided by any number m and n, so they do not have any common divisor other than 1. So again, the same thing, we can square both sides in this manner, so it will be m squared equals 7n squared. Okay, now we have the equation that is m squared equals 7n squared, and we may have two cases here, right? So case 1 is that if n is even. So if n is even, right? So if n is even, then 7n squared, it will be also even number. So then if n is even in this case, then 7n squared is also even. All right, because if we have even number and we square the even number, then for instance, let's say we have n equals to 6, it's an even number, and then n squared equals 36. Again, this is even, and if we want to find 7n squared, that is we want to multiply 36 by 7, again we are going to get an even number. So we have 7 6 42, 2 4 7 3 21, and 4 2 52. So we can see that this is even number. So if n is even, then n squared is also even, and then therefore 7n squared will be even. And we can see that this 7n squared equals m squared, which means that if this number is even, then this number is also even. So we can say that m squared is also even. Okay, so if m squared is even, then m is even, because we already uh, uh, concluded in the previous question that if m squared is divisible by 2, then m is also divisible by 2. So here also, if m is also even, if m squared is also even, then m is also even, which means that even number is divisible by 2. So if n is even, it's divisible by 2. M squared is even, then m is also even, and m is also divisible by 2. So which means that both m and n have common factor, which is a contradiction. M and n have common factor, which is a contradiction, right? So because in our assumption we said that m and n have no common divisor other than 1. That means they don't have any common factor. Then the second case is case number 2 is that n is odd. Case 2, n is odd. Okay, so now in this case, if n is odd, then 7n squared is going to be odd. Okay, because if n is odd, then square of n will be odd. For instance, take 3, its odd number, its square is 9. And if we multiply this n square, that is 9 multiplied by 7, that is odd number multiplied by odd number, we are going to get an odd number. So 7n square is also odd, which shows that 7n square is odd. So if 7n square is odd, then this, by this equation, that is 7n square equals to m square, we can say that m square is also odd because both are equal. So m square is also odd. Okay, fine. Now what we can do here is that we can write if both m square, okay, and m square is all odd, this implies m is odd. So now we can write both m and n as odd numbers. So we can write m equals 2p plus 1, which means that 2 times some integer plus 1, this will always be odd, right? Any integer, if I multiply 2 with any integer, it will be an even number, and even number plus 1 is odd. And n equals 2q plus 1. Now plug here in this equation number 1. So we will get 7 times 2q plus 1 squared equals 2p plus 1 squared. And then if we square this number, that is 2q plus 1, we will have 4q squared plus 4q plus 1 equals 4p squared plus 4p plus 1. And it will be 28q squared plus 28q plus 28 equals 4p squared plus 4p plus 1. Okay, so sorry, this is not 28, this is 7. 7 times 1 is 7. All right, so we can bring this one to the left side and we will have 28q squared plus 28q plus 7 minus 1, it is 6 equals 4p squared plus 4p. We can divide this whole equation by 2. So we will have 14q squared plus 14q plus 3 equals 2p squared plus 2p, which we can write 2 times p squared plus p. Now, on the left hand side, we have the number that is 14p squared plus 14q plus 3. Now consider this number and check whether this number is even or odd. Now this element is 14 times p squared, so this will be always be even because it's multiplied by an even number. So even number multiplied by an odd number uh, will give us, okay, p is odd. Okay, so p squared is odd. Oh, let's see. Okay, we did not assume anything about p. Okay, and we assume about m and n. So 14 times p squared. What about this number? What we can say about this number? If suppose if p is odd, if let's say if it's 3 or 5 or something like that, so if we multiply its square by 14, so we are going to get even number, right? Again, similar here. Okay, this is not p square, sorry, it's q square. So same thing happens here. So these two numbers are even. Even plus even, this whole thing is even. But if we add 3 with any even number, we are going to get an odd number. So the left hand side is odd number. And on the right hand side, we have p squared plus p, whatever this number p squared plus p is. But when it will be multiplied by 2, we will get an even number. So this is a contradiction that that an odd number is equals to even number. So this is contradiction. So we saw that this contradicts our assumption that we assumed, contradicts the assumption because it's not possible that an odd number is equals to even number. So in both cases we saw that the square root of 7 is an irrational number. So the conclusion is that the square root of 7 is irrational. And we can also solve some other problems using these methods by contradiction. Okay, so now we are going to talk about the bounds. That is the lower bounds and the upper bounds. We will see what actually we mean by the lower bounds and the upper bounds.